Alrighty everyone, welcome back to Acorn's Academy. In this video, we are going to talk about the E2 reaction. Our previous videos, we've gone over the SN1 and the SN2 reaction, compared and contrasted their similarities and differences. So today we are going to shift our gears over to elimination, okay? So as always, we're going to start with the name, okay? The name E2. Now, as we go through this video, you will recognize that E2 and SN2 have a lot of similarities. The biggest of which is the fact that they both have this 2, right? So the 2, just like how in SN2 it meant bimolecular, it's the same situation with E2, okay? The 2 means bimolecular. The E here, correspondingly, means elimination, okay? An elimination reaction is any reaction in which we are forming a pi bond, usually a double bond. Okay, not always, but usually a double bond. And we can see that right here, we're forming this alkene. Okay, that's our product. Now, there's this additional term here, this beta, and I will come back to what that is in a little bit. Okay, first let's go ahead and look at our reaction scheme here. Pretty generic E2 reaction. We have this secondary alkyl halide, this alkyl bromide, and upon treatment with strong base, okay, upon treatment with strong base, we get an alkene. Okay, so I treat my alkyl halide with strong base, and I get an alkene. Okay, so let's go ahead and address the beta part of this name here. So anytime I have an alkyl halide, the carbon that the halogen is attached to, that is always going to be considered our alpha carbon. Okay, that's our alpha carbon. Whatever carbons are next to the alpha carbons, those are called beta carbons. Okay, so if I have beta elimination here, what's happening is my base is going to pick up a proton from one of these beta carbons. Okay, we're going to pick up a proton from one of these beta carbons. So I'm going to go ahead, we're going to switch back to our table. Okay, we've been filling out this table over the course of the last couple of videos. And you'll recognize again, kinetics are bimolecular, and our base strength here, again, this is elimination, so we're talking about bases now. And we have some prototypical strong bases here, hydroxide, any sort of alkoxide, and NH2 minus. Okay, negatively charged nitrogens are very, very strong bases. So those are some examples there. Now, mechanism, just like SN2, is concerted. Okay, this is a concerted mechanism. Our substrate, you'll notice here that we're starting with a secondary alkyl halide. The reality is that, in theory, E2 elimination could happen with any substrate. Now, this does also depend a little bit on what your professor says. I was taught that any of them could work, but some would be preferred, and we'll get to that in just a little bit. But in the grand scheme of things, any substrate could work here. Okay, we already covered our base strength. Stereochemistry is a little complicated, so again, I'm going to write it out first, okay? The stereochemistry is something that is known as beta anti-periplanar, okay? We have to have beta anti-periplanar stereochemistry in order for this E2 elimination to work, okay? And I'll explain what this word means in just a minute, okay? And then lastly, the solvent type. You'll notice we don't have a solvent. That is because any solvent could really work here. Okay, any solvent could work here. All right, so I'm going to go ahead and go through this mechanism, and hopefully the beta anti-periplanar and all that jazz will start to make sense. So I'm going to redraw this alkyl halide, and as I'm drawing this out, you'll notice that in the reaction scheme, I have 2 hydrogens highlighted in different colors, okay? I have a blue hydrogen and I have a red hydrogen, okay? Now, this difference is important because if you look at the product, okay? If you look at our product here, the blue hydrogen is the only one left. The red hydrogen is gone. So, I want you to look at this red hydrogen and tell me what you notice, okay? You might notice that this hydrogen right here is on the opposite stereochemistry to the halogen, Okay, see how the bromine here is wedged? That red hydrogen is dashed. Okay, that is what beta antiperiplanar means, is that it's on a beta carbon with the opposite stereochemistry to the halogen. Okay, opposite stereochemistry to the halogen. That's the one that we're going to eliminate. That's the proton we're going to take off. So as I'm doing this mechanism, I need a strong base, so we'll just go with OCH3 minus. That'll do the trick. Okay, something like this. And what we observe, let me get a different color here. We observe that this blue proton is the one that we have left over. So what my base is going to do, my base is going to pick up a proton. Okay, you may recognize this from your earlier OChem chapters. The bases pick up protons. So I'm going to pick up this proton, and then this bond, I'm going to kick that electron density in between these two carbons, in between my beta and my alpha carbon. And I'm going to use the energy of forming that bond to kick off my leaving group. Okay, so just like with substitution, we do indeed have leaving groups. Okay, just like that. We have our beta elimination. We eliminated an antiperiplanar proton, and we have formed a pi bond. And I guess I'll write out some side products here. One side product we get is this Br minus, and then the other side product we get is methanol, CH3OH. Okay, so now what I'm going to do is I'm going to write another example here, because this is something we have to talk about as well. So part of what contributes to the kinds of alkenes we get in an E2 reaction relates to the stability of the alkene, okay? And we saw this right here because we also have beta protons here at this carbon, right? But we didn't eliminate any of those, because if we did, we'd get a primary alkene or a monosubstituted alkene, whereas here we have a disubstituted alkene, okay? This is disubstituted alkene. Now, sometimes, depending on our base, okay, the base does need to be strong, but depending on how bulky that base is, we might actually get a different product, okay? So I'm going to draw a base here. You may or may not recognize this molecule. This molecule is known as tert butoxide, okay, tert butoxide. Tert butoxide is a strong base, but it is a bulky base, okay? What that means is if tert butoxide has the option, it is going to prefer to take the less sterically hindered proton, okay? We want to take the less sterically hindered proton because the base has these three methyl groups. These are very, very bulky, and they're hindering the base from really getting in there and taking this proton that we took last time. So in order for us to actually get an alkene and still, make the process of elimination, but also make sure that we don't encounter too much steric hindrance, we're just going to pick the proton that's on the less substituted carbon, right? That's a good way to think about it. So I'm going to pick up this proton, and same deal, kick that bond in to form the alkene, use that energy to kick off the bromine, okay? Just like that. So I end up with something that looks like this. Okay. Now you'll notice this is our product that we got the first time. Okay. This is our first product right there. And this is our second product. So these products kind of have names. Okay. They have like designations. If I use a small, or more properly, an unhindered base, okay, if I use an unhindered base, I'm going to get what's known as a Zaitsev product. Okay, a Zaitsev product. Okay, so this right here, this would be a Zaitsev product because it's an alkene that is more substituted and it comes from a pretty small base, okay? Methoxide is very unhindered. On the other hand, if I use a large or a bulky base, okay, a base that does have a lot of steric hindrance, again, a typical example here is just terbutoxide. Okay, terbutoxide is the one that most students learn. I'm going to get what's known as a Hoffman product. Okay, so my major product with a unhindered base is Zaitsev, and my major product with a bulky base is the Hoffman product. Usually, the Zaitsev product correlates with a more stable alkene, usually, okay, keyword usually, and the Hoffman product usually correlates with a less stable alkene. All right, stable is actually not the right word here. I'm going to go with substituted. Okay, more substituted alkene, less substituted alkene. Okay, take a second here just to organize this. All right. So I think that just about covers everything that we really needed to cover for the E2 reaction. I hope you guys found this video to be helpful. I do hope you'll stick around. I'm going to do the E1 video soon. And yeah, please leave a like and let me know any feedback you have in the comments below. And I will see you all in the next one. Take care.